Thank you very much, Ian. Hello, good morning to Europe, good evening to Asia Pacific, and sleep well to the Americas. As Ian said, my name's Yuval. I'm a postdoc at Macquarie University here in Sydney, Australia. I'll be speaking about compilation of fault-tolerant heuristics, quantum heuristics for combinatorial optimization. So I'd like to try to summarize my talks in one slide at the beginning so that everybody sort of knows what the point is. So the point of this paper, and it is a large paper, is that quadratic speedups appear insufficient for early quantum computers to beat classical computers at combinatorial optimization. So I'll spend a bit of time explaining that, but I, at this moment, want to just highlight the word appear. We are giving evidence for our conclusions. We are not proving our conclusions. This is the team responsible for the work. So from the top left, that's me, Yuval. I guess you can see me on the Zoom. I'm a postdoc of Dominic here at Macquarie University. Together on this, I worked together on this project with Dominic, of course, as well as Pedro Costa, who is another postdoc of Dominic, and Louis Tessler, who is a graduate student of Dominic. This work is a collaboration with Nathan Wiebe, who's now at the University of Toronto, and a team from Google. So that's Craig, Gidney, Hartmut, Neven, and Ryan Babbush, who led the project. So I split the talk roughly into two pieces. The first piece is aimed at people who haven't seen our work. So I'm trying to give a good high-level overview. So there's not that much technical detail on this first part of the talk, but then I'm hoping that this way everybody will understand what we're talking about. And then because this is QIP, I'm trying to spend some time at least on some of the technicalities in our work. And I've chosen depth rather than breadth. So I am presenting a specific technique that we developed for this piece of work that we think is going to be very likely useful for many other numerical approaches to quantum algorithms. And then I'll finish off with some conclusions and some opportunities for further work. So I'll start with some motivation and background for combinatorial optimization and what's been done before. So combinatorial optimization, I was hoping to give a good technical introduction, but I think that it's best to just give a rough picture of what it is that a combinatorial optimization problem involves. So for us, we are imagining that we are given a 2 to the n by 2 to the n Hamiltonian operating on n qubits, and we're promised that this is a diagonal Hamiltonian in the computational basis, and we're just trying to find a ground state of this Hamiltonian. We're happy to choose one essentially at random. So this is a somewhat strange problem formulation if you know the literature on combinatorial optimization, but it does map over to what we'd expect. So there are some fairly famous examples of combinatorial optimization. So for example, the traveling salesman problem, the minimum spanning tree problem, and the knapsack problem. And the approaches that we're looking at are fundamentally heuristic. So we are not aiming to find the true ground state with a guaranteed high probability or even perfect probability, 100% probability. What we are doing is we are thinking about how these problems would appear in practice. And in practice, we would expect to be satisfied with an approach that is probably going to give us a nearly optimal solution. So the intuition behind this is to say that if we were really solving the traveling sales problem in real life, it's good enough for the traveling salesman to come up with a pretty efficient route, and it doesn't really need to be optimal. As long as it's pretty close to optimal, we're probably going to be satisfied. And the prototypical classical method of doing this, and I say prototypical advisedly, is simulated annealing. So this is what I'm calling a heuristic approach, which is to say, this is some idea that I am bringing into the problem. It is not intrinsic to the problem, but I'm using my idea to design some algorithm that is likely to work out in cases that I am likely to encounter. So it's, of course, very difficult to give provable statements about this, but this is how things work in practice generally for combinatorial optimization. And combinatorial optimization has many practical applications, much as the quadratic formula has many practical applications, but just to highlight a few, there's logistics, supply chain optimization, water distribution, and practically anywhere you can imagine sticking the word optimization. So it's a natural place to look for useful quantum algorithms. So when we are studying combinatorial optimization, we are studying fairly specific cost functions. So that is to say, ways of measuring how expensive or cheap a solution is. And we're modeling this using Hamiltonians. That is why I formulated this in terms of diagonal Hamiltonians. And we looked at 4 families. So from most general to most specific, the L term spin model is a weighted sum of, and the L refers to the number of terms in the sum, and a weighted sum of L different products of Pauli Z operators. And remembering that this has to be in the diagonal basis. This has to be diagonal on the computational basis. And these can be arbitrary products of the Pauli-Z operators. Then that's quite a large class of possible models. So it's helpful to look at something a little bit more specific than that. So we looked at quadratic unconstrained binary optimization, or QUBO. And this is where the products of Pauli's are guaranteed to be only between pairs of qubits. So you can think of this as being checking to see the parity of different pairs of bits and then assigning some kind of a weight to it. So maybe you prefer the two bits to be in the same, or maybe you prefer the two bits to be different, and the QUBO model can handle this. And QUBO is known to be NP-hard, and it is a subproblem of L-term spin model. Even more specifically, we looked at the Sherrington-Kirkpatrick model. So this is where we're guaranteeing that the weights are plus or minus 1. So to take the example of before, then we can imagine that there are two, we are looking at pairs of bits, and we are asking whether the parity between them is 0 or 1. And we assign either a +1 if they're a +1 to one of those cases and a -1 in the other case. And different instances will give us different choices here. And then the last one we look at is so specific that in fact there's only one instance per choice of capital N. This is the so-called low autocorrelation binary sequences problem, or LABS. And this is a hard subproblem of the L-term spin model. And the best known classical algorithm scales exponentially in capital N. And it's in fact only ever been solved for n less than 66. So it's quite a nice test case. You can imagine that if we ever find a quantum algorithm that's able to solve labs for n greater than 66, then we've found something that a quantum computer can do that's useful, is maybe a stretch, but interesting. So there are quantum heuristics out there. And so I'm not going to be able to give a complete overview of the heuristics that we looked at. In particular, I shoved most of them into this can of worms down the bottom. But to give an idea of what a heuristic can be like, let me just talk briefly about the direct amplitude amplification approach. So we can imagine the combinatorial optimization problem is like a search problem over 2 to the n possible different bit strings. So we could imagine just exhaustive search. We can look at each of the possible bit strings, ask what is the energy of this bit string, and then figure out which one's the lowest one. So that's like a search problem. And so then because it's like a search problem, we can imagine finding a Grover-like speedup for this, and that would give us a square root speedup. Now, this is a really dumb approach, and we all know it's a dumb approach. And the reason it's a dumb approach is because it's treating the problem as unstructured when in fact we're expecting a lot of structure. So if we have extra information, we should be using it. It would be dumb not to, and hence this is a dumb approach. With that said, it's a good reference point. Another common heuristic these days is the quantum approximate optimization algorithm. So in the quantum approximate optimization algorithm, the idea is to alternate between evolution under the problem Hamiltonian. This is the diagonal Hamiltonian that one starts with when defining a combinatorial optimization problem, and some driver Hamiltonian, which is chosen specifically not to be diagonal. So the idea is that the driver Hamiltonian is supposed to create superpositions of possible solutions where none existed before. And then the concept underlying quantum approximate optimization is to alternate between these evolutions. So you evolve under the problem Hamiltonian, then you evolve under the driver Hamiltonian, then under the problem, then under the driver, and so on and so on. And then you hope that you have managed to drive the state of the system into a ground state. And there's several cautions that one should take with this approach, and maybe the most important one is that there's a more asymptotically efficient classical approach known to at least the original version of this algorithm. So I'll offer this reference to a paper by Barak et al. But there's a reason that people still study QAOA, and that's because QAOA may have better constant factors, at least in relatively small cases, and it may be robust enough to error that it could be executed on NIST hardware and provide useful answers. So just because there's no asymptotic speedup, that doesn't mean that there isn't some potential use case for this idea. So that's why this still continues. And then many of the heuristics that are being studied are in terms of adiabatic algorithms or quantum simulated annealing, which is different from quantum annealing. Quantum simulated annealing means that it's simulated annealing as simulated by a quantum computer. So it's a classically understandable concept, but the simulation part of it is done on a quantum computer. And it's a giant can of worms, and quite frankly, I think that the research there is still fledgling and lots is still to be done. I'd say we're in the early stages of it. And fortunately, I don't have to go into it too much because we're not really adding anything to the story, at least not adding anything substantial. We're really focusing on compiling ideas already found in the literature, and it's really ongoing work to develop better methods. Okay, so now that I've given the background, I want to explain our approach to the problem of figuring out how well a quantum computer would do combinatorial optimization and what our results ended up being. So as I said, what we do is we take these ideas that are existing in the literature and we spend 2 years, including a large part of our COVID lockdown, trying to compile these things into explicit quantum circuits. And the compilation, just to summarize the fairly long story, is that it involves 3 stages. So the first stage is to design an oracle for the cost function. So that's to say that if I want to know whether a candidate solution to the optimization problem has this cost or that cost or whatever, I need some kind of a quantum subroutine that's going to tell me that cost. And there's a couple of different ways that this oracle could return that information. It could be simply writing down the information into some other register, or it could be reporting the information as an overall phase to the input register. Then once we have this so-called oracle for the cost function, then we need to design a quantum circuit that uses that oracle in order to perform a single step of some given heuristic. So for example, QAOA. And then once we do that, we then estimate the runtime on a circuit code quantum computer by estimating the number of Toffelees. The reason we count Toffelees and nothing else is because Toffelees and other non-Clifford gates are considered significantly more expensive in the surface code than any Clifford gate is. And that's because of the needs to do magic state distillation in order to execute non-Clifford gates. So because this is such an immense cost relative to the cost of doing Clifford gates, then we tend to estimate runtimes by simply counting the number of Toffelees. So by carrying out this strategy, the results will therefore tell us how many heuristic steps can be performed in a given amount of time. So we particularly report in terms of 1 day or 1 hour. What they don't tell us is how many steps of each heuristic are needed in order to achieve approximate success with some probability. And what that means is that we cannot directly compare the results for different heuristics. These are simply performance indicators. And the reason we can't compare these different approaches directly is because different approaches may require a different number of steps to achieve the same results. So we are only saying how many steps can be performed in a given amount of time. We are not saying how many steps are required to get to a solution. And that's why the numbers cannot be compared. I highlight this because you're about to be overwhelmed by numbers, and I want you to understand that you can't really compare these numbers. So here's the overwhelming amount of numbers. And like I said, this is how so here in Sydney, we are no longer in COVID lockdown. Things are actually pretty normal here, except that we can't leave the country. But we did have a lockdown, and this is what we did with it. And I'm not going to make you suffer through it. I'm going to give you a simplified version. And in the simplified version, here we're highlighting just 2 of the 4 different kinds of problems that we looked at. So on the top is SK, and on the bottom there's labs, so SK Sherrington Kirkpatrick. And then the algorithm primitives we look at are amplitude amplification is the Grover-like approach. QAOA is QAOA. Hamiltonian walk is an adiabatic approach. And QSA stands for quantum simulated annealing. And there are a couple of different approaches to that. And again, I remind you, you cannot compare these numbers directly. And of course, the numbers you expect to be different between SK and labs. And this is about the execution of the cost function. So it's hard to know what to make of these numbers in the absence of some kind of comparison to the classical world or to something that we can put our hands on. But the box numbers, so the ones which are QSA with what qubitized means qubitized metropolis Hastings approach, which I'll say a little bit more later. And this can be kind of sort of compared to classical simulated annealing via the metropolis Hastings algorithm. Now, I say kind of sort of because it's actually a little bit of a question mark how many annealing steps are required to get to a solution. And this is one of those discussions that's probably best left to the round table. But the thing to notice about those box numbers is that I, one Saturday afternoon, wrote a fairly simple piece of Python code and ran it on my laptop. And my laptop's pretty good. It's a 2019 16-inch MacBook Pro. It's i7 processor. It's a decent laptop, but it is a laptop. And it's beating what we estimate for the quantum computer by 2 orders of magnitude at least. That's not encouraging. And that's a way to interpret the rest of these numbers to say this does not look very encouraging. And you might say, oh, look, the Hamiltonian walk, that has a 10 to the 5 rather than 10 to the 3, at least in labs situation. But you expect a lot more steps there, and you don't expect that to buy you anything. So that's where we get our sort of depressing conclusions about the prospects of doing combinatorial optimization on a quantum computer. So before I summarize those conclusions, I just want to highlight maybe one of the key techniques in our paper that's likely to be useful to other people. So the motivation behind this technique is that when we are doing heuristic-based optimization, in fact, many numerical algorithms are actually bottlenecked by the need to calculate certain functions. So in the case of these optimization algorithms, we need to calculate functions of the energy or the cost of the candidate solution. But because our approach is heuristic, the choice of functions that we made was kind of arbitrary, and we sort of waved our hands in some way when we chose those functions. So we don't really expect that we need to calculate those functions, pardon me, very precisely. So we're looking for a way to approximate the value of the function that is, we're perfectly willing to trade off accuracy. We don't care about the accuracy of the function approximation. What we care about is speed. So we're happy to trade accuracy for speed. So our approach is based on the linear interpolation between lookup points. This is a very old idea, so you might know that, for example, in the olden days before there were automatic computers, people might calculate a logarithm by looking up known values of the logarithm in a lookup table and then carrying out some fairly simple calculation to figure out the logarithm of the number they really cared about. So this is the inspiration behind our technique, and it's a very general technique because this is used ubiquitously in many other numerical algorithms. So to explain how that works, it's important for me to go back to a concept that Dominic talked about earlier in the conference, and that's the concept of QROM. So my particular explanation of QROM is that it's a quantum data structure. And what it is it's a list in the classical sense. It's a list of classical data, but we're allowed quantum access to the entries of the list. So we are given some list where that's of length capital L, and the 0th entry of the list, starting from indexing by 0, as any computer scientist should. D sub 0 is the 0th element of the list, and then D sub 1 is the first element of the list, and so on up through the capital L minus 1 entry of the list. And then, so then the idea is that classically we would imagine querying the list with an index little l, and the response should be the data D sub L for the query little l. So then with the QROM, the idea is that we can query with a superposition, as I've indicated with this equation. So I can I can do, for example, a superposition of L equals 0 and L equals 5, and produce in my data register a superposition of D sub 0 and D sub 5. And the main trick underlying QROM is that there's a clever iteration through possible input. So if you tried to implement this idea in the naive way, you'd come up with a Toffoli count that's order capital L log capital L. You quickly realize that you don't need a number of Toffolis that scales with the amount of data to be output, because you can just write those out with C naughts. And again, we're in a cost model where C naughts are, because they're Clifford gates, are free. But it turns out that there's a cleverer way to iterate through the possible values of little l, such that there's only a need for order capital L Toffolis. And in fact, if you use a particular technique that we've come to call Gidney's joint trick, then it turns out that it's exactly capital L Toffolis. And to give a sense of how this works, then I've just indicated where the iteration in little l is happening in the diagram, which is from a paper by Dominic and Ryan and some others in 2015. Sorry, not 2015, 2018. So the way that we're using the QROM is to look up the points in a function. So the idea is that if we are going to evaluate f of x, we can approximate this by evaluating f of x sub l for some known value of x sub l that's close to x. And then we add to it some slope that depends on L times the difference between x and x sub L. So the idea then is to use the most significant bits of the input x in a QROM lookup to figure out what we should use for the values of f of x sub L and for m sub L. Then we take m sub L, we multiply this to the least significant bits of x, which are the same as those of x minus x sub L, because we're just ignoring the bits that are going to turn into 0 when we do that subtraction. And then once we've done that multiplication, we add the result of that multiplication to f of x sub L. And so that's how we can do this linear interpolation. So the Toffoli complexity of this is ignoring the cost of the arithmetic, which we do cost out in our paper. The Toffoli complexity goes as the number of lookup points. And I'll briefly point out that the error of this thing depends on the second derivative of the function being approximated. And it turns out for the functions that we care about, our second derivative is usually quite small. So I won't go into details about why these are the functions that we particularly care about, but because these are the particular functions that we care about with an exponential decay to them, we can actually optimize our QROM lookup and perform really a variant of QROM in order to sample from this in a way that we can reduce the Toffoli cost and still get a reasonable approximation to our function. And we give numerics in our paper suggesting that this is a reasonable thing to do. So the idea is to look up from the QROM, not for each possible index L equals 0, L equals 1 up to, in this case, L equals 15, but we're only going to look up for L equals 0, 1, 2, 3, 4, 6, 8, and 12. And the way this works and the way it's saving Toffolies is that the bottom line over here sort of corresponds to the original diagram, where again, the C naughts at the bottom of these Gidney elbows are iterating the value of L by 1. But then when we go up a level, we're iterating by steps of 2, not by steps of 1. And then when we go up to the next level, again, we're iterating by steps of 4, not steps of 2. So you can reason this out and realize that you're making quite a savings in terms of the cost of the QROM lookup. And the promise here is that we are looking up data where it doesn't matter if it's the data corresponding to entry 4 or the data corresponding to entry 5, because you presume they're the same, which is justified for the specific functions that we're studying. Okay, so that's, I feel, about as much as I can go into in terms of those technical details, but I hope that gives a reason to read our paper or ask questions in discussion time. So I'll just move on to the conclusions, which I think that many people are probably going to be interested in, and maybe some sort of hope for the future. So the basic lesson here is that based on our analysis, it seems as though quadratic speedups for heuristic-based optimization are probably not enough to see early quantum computers beat even my present-day laptop. These numbers are mostly falling from overheads due to the fault-tolerant architecture. So this is the need to correct errors faster than they occur in a noisy system. And then the natural response is to maybe look for more efficient fault tolerance methods, or maybe try to reduce the hardware noise. But I mean, I think we all know that everybody's working very hard at that anyway. The other more depressing conclusion, at least depressing for some people, I don't care, I love this subject regardless of whether we have a quantum computer, is to just give up on the idea that an early quantum computer at least will be useful for something involving quadratic speedups. So that's the depressing side of the story. The more hopeful side of the story is that there still may be better than quadratic speedups to find. I would say that there's some hope for that, but it's not an easy question. And so it really needs deeper research than we've been able to carry out even over the last couple of years. So one thing we did try was we attempted to chain together quadratic speedups, but that failed pretty quickly. And it's not easy to do it effectively because you need to do quite a bit of research into exactly how these heuristic methods are going to be working for a given combinatorial optimization problem. And I'd also comment that our conclusions really are a little bit tentative in the sense that we do need more careful analysis of the relative merits of different quantum heuristics, and I might very strongly add more thorough comparison between classical and quantum approaches, and in particular quantum simulated annealing. Again, it's quite a deep topic and it's quite rich for further work. So I'll close with just a little some offers or further reading. So our full paper can be found on the archive and is also published in PRX Quantum. The line editors of PRX Quantum did an absolutely heroic job typesetting this paper, but unfortunately it's a very long paper and quite difficult to typeset. So there's some parts of the paper where we're not that happy with how it ended up. But so if there's some equation or something in our paper that looks a little bit strange, please check the archive version before coming to complain to me or anybody else, because maybe it's just some complication in the typesetting process. If you want to hear more from the Google people specifically about the limitations of quadratic speedups, they've got a paper on the archive as well. I would comment that we are not really the first to say that quadratic speedups are kind of a dangerous bet for quantum computing. So I'll point specifically to a paper by Campbell, Carana, and Montanaro. So there's the archive reference, there's the DOI. It was published in the journal Quantum in 2019. And I also very strongly recommend any good textbook on simulated annealing, because there's really some low-hanging fruit for anybody who really understands simulated annealing. It's just that I'm not an expert, and I haven't talked to too many experts just yet. Thank you very much.
Thanks a lot, Yuval, for the very nice talk. Let me relay a question from Slack. So the question comes from Timo Eckstein, who asks, is there some particular reason why you restrict yourself to diagonal Hamiltonians in the problems?
Do you mean that's referring to? I'm sorry, just a second.
This was at the very beginning of your talk.
These Hamiltonians here, right?
Yes.
Is this? Yeah. So So I'll first say that we need to restrict ourselves to some kind of Hamiltonians because we are not reporting results in terms of oracle queries. We don't get to do that. We have to actually figure out what it costs to calculate the cost of a given candidate solution. So we need specific Hamiltonians in order to come up with ways to calculate the cost function. So we're selecting these as representative of possible optimization problems that one might encounter. And then we go through quite a bit of detail in how we're going to calculate this on a quantum computer. So again, the reason we focus on these is because we're not taking the shortcut of counting oracle queries.
Thanks a lot. I have a question myself. I'm afraid a bit of a naive one. The way you benchmark your compiled circuits is by the number of toffolies.
Yes.
How does this compare to like the depth of the circuit? I mean, couldn't you like use some techniques in order to make it shorter?
Yes, and so and that's a good chance to talk a little bit about how we're getting the numbers that we are. So we're being a little bit naive about this because we are assuming that all toffolies must be carried out in sequence. And so the idea is that in the surface code, we're supposed to have what they would call a T-gate or a toffoli gate factory, which prepares a magic state and then does some stuff to it in order to simulate a toffoli gate or a T-gate or whatever the non-Clifford gate might be. And we're assuming that we have only one such factory. So all toffolies must be carried out sequentially in our compilation model. Now, we know that's naive, but it's also quite a bit of work to do what you described, which is to find some way to optimize on depth by parallelizing. And frankly, it's not something that's reasonable to do by hand. It's something that needs to be automated, and I think the tools don't exist yet.
Makes sense. Thanks a lot. Good. So I guess there are no more questions. So thanks again, Yuval, for a very nice talk.
Thank you.